I'd like to introduce our final speaker in this session, Associate Professor Neil Walton. Associate Professor Walton is a reader in mathematics at the University of Manchester. His research is in applied probability and principally concerns the decentralized minimization of congestion in networks. Previously, he was at the University of Amsterdam and has had research visits at Microsoft Research Cambridge and ETH Zurich. He has won Best Papers Awards at ACM Sigmetrics and was awarded the 2018 Erlang Prize by the Informs Applied Probability Society. Associate Professor Walton has recently published on a range of topics highly relevant to this workshop. So it's great to have him present this tutorial on the role of information and learning in the stability and optimization of queuing systems. So I'll pass over to you, Neil.
Okay, hello, you can hear me okay?
Yeah.
Yeah, super. Okay, great. Thank you very much for having me, Nikki, and also to Michelle and Peter and the other organisers. So this is originally written as a kind of tutorial for the kind of Informs tutorial series. So it's was written this year as a kind of overview of some views of how kind of learning theory can kind of fit in potentially with queuing theory. So we're kind of going to have a few examples, but also have some literature reviews. So it's useful. Michelle's talk earlier where he reviewed some aspects that we're going to cover as well. Okay. And this is a joint work with Quang Zhu, who's at Stanford University. And there's an article which you can download from the archive as well, where you can grab a copy of the paper and sort of literature review associated with this if you want to pick up any of the references that we discuss. Okay. Okay, so our aim is to give a summary of the role of learning, learning theory and information in the context of queuing theory. So we're hoping to kind of discuss literature that's out there and kinds of results that bridge learning theory with queuing theory. We'll have some sort of new, in inverted commas, results, but the intention of this is really to make connections, to review things, but obviously we're going to end up being a little bit non-exhaustive at the same time, so that there will be things that probably end up missing out, and I'll try to give pointers to those as we go along. Okay. So as Michelle mentioned, queuing systems arrive in lots of situations, in communications, manufacturing, healthcare, supply chain, transportation as well is not on the list. There's plenty of other things that we could include on the list there. So it's a very relevant area. How we compare it with other areas of operations research, such as revenue management, in those areas, there are well-established connections between, say, information, where, say, a customer might arrive to an online shopping system and you'd have information about the context of that customer and the search criteria that they conducted. Learning, where we might try and estimate certain parameters associated with those contexts, for example, calculating some sort of maximum likelihood estimator. And then decision-making, where we might try and choose some price in order to charge that customer fee for purchasing goods or services. And that price would typically be, say, a certainty equivalent price, but with some error associated with that, usually decided by some sort of confidence interval. Okay. However, the same isn't really true for queuing systems. And part of the reason for that is, well, one, because we haven't developed all the theory that needs to be there yet, perhaps, but also because maybe it's a slightly harder problem, because in revenue management, when the customer comes, they purchase their products, they go away, and the next customer arrives. And people don't, the system kind of refreshes itself in a way that wouldn't in a queuing system, because you're trying to keep track of inventory or jobs or queues within your system. Okay. So I'm going to kind of talk about 4 different topics. One is going to be about the theory of kind of approachability, Blackwell's Approachability Theorem, and MaxWeight, which we could think of fitting within the topic of adversarial learning and also online learning. Then we'll discuss online learning specifically in the context of queues, and we'll give an example there where we can put that theory within the kind of supervised learning theory. Then we kind of slightly switch gears a little bit and discuss about the role of information and state information making decisions in queuing systems and how that seems to be an important feature. And so we'll kind of discuss that. Then we'll discuss kind of more recent work on reinforcement learning in queuing systems, which is kind of, so earlier in the summer, Mengdi Wang, Nicholas Gast, and Guang and myself organized a workshop on reinforcement learning in queuing systems, and we sort of review some of the papers that were there and also some of the challenges that occur within that area. Okay, so that gives a kind of rough overview. The first two parts are going to be more sort of examples, giving sort of a specific example where kind of a learning type theory can be used to apply to a queuing system. The last two parts are sort of perhaps more literature review and discussing, potential open problems and issues. Okay. All right. Good. So let's get on with the first bit. And please, as we go along, you're welcome to use the chat. I've got an extra window up here where I can see the chat part. So if you ask any questions, I'll try and answer those as we go along. Okay. So we're going to discuss about Blackwell's approachability theorem, and in particular how it relates to a specific scheduling policy, which is very popular in queuing, called the MaxWeight policy. Okay. So Blackwell's approachability result is a classical result from the 1950s, and it concerns the control of a sequence of rewards, a vector of rewards towards some convex set. Okay, and I'll describe that in more detail in a minute. A direct consequence of Blackwell's result, which Blackwell published in a short 2-page paper at the International Congress of Mathematicians, he proved that you could use his policy and ideas in order to design online learning and sequential learning algorithms. Okay? Sort of online learning has grown to be quite an important area. And in fact, sort of about 10, 15 years ago, it was proven by Bartlett, Abernathy, and Hanan that in fact online learning is equivalent to Blackwell approachability. And then you have that some of those authors, like Hanan, have gone on to look at sort of adapted regularization versions of these and develop the Adagrad optimizer. And now Adagrad and Adam RMS prop are part of the kind of standard toolkit for optimizing neural networks these days. Okay, so this is kind of direct line through that kind of modern learning theory. On the other hand, what we're going to argue here is that, Blackwell's result is a pretty useful result also in queuing, and that actually a set of policies which are quite famous in queuing, called the MaxWeight policies and BackPressure policies, can actually be the reason that they have what are quite robust stability properties in a queuing system as a consequence of Blackwell's original result. Okay, and so we can kind of make these connections between different areas of learning with existing queuing systems, okay, and existing algorithms that we know about. Okay, so I'll start by describing Blackwell's approachability theorem, then discuss about kind of online learning, and then we'll go into talking about switch queuing networks and MaxWeight policies. Okay. So what's Blackwell's approachability theorem? It's a classical result in learning and control and game theory as well. It's a vector generalization of a result in game theory, which you might have covered in your undergraduates, called the Minimax theorem. Okay. So the setup's like this, that we make a decision. That decision belongs to some convex set. We can think of the decision being, say, a probability on the probability simplex for different actions or choices. Okay, you have an adversary also that makes a decision as well. And then as a combination, a linear combination of your decision and the adversary's decision, we get some reward, Rij. Now this reward isn't one-dimensional, it's a vector. Okay, so we're getting some vector reward, and RDA is the vector reward that we receive for decision D and adversary decision A. Okay. And then what we're interested in is the performance of the average reward vector over time. So we can look at the average over time, sum up the rewards over a sequence of decisions and a sequence of adversary decisions. So here we think we've got the discrete time system where each time I just make a decision based on the past observed rewards, decisions, maybe adversary decisions. And the adversary also makes a choice A as well, perhaps based on the previous information. Okay. And then over time, we clock up the kind of average reward that's happened over time. Okay. Approachability holds if we can navigate those average reward vector towards some convex set Z. Okay. So in particular, we can say this convex set Z is approachable if this average reward vector over time we can get it to get closer and closer to this convex set Z. Okay, so we can think of our decisions are trying to push us towards the convex set Z, but the adversary may or may not be pushing us away from that convex set. And is there a way that we can make decisions that make us go closer to this set Z? Okay, so that's the kind of basic question of Blackwell's result. And what Blackwell does is essentially give a necessary and sufficient condition for this to hold. Okay, so Blackwell proves in, I think, 1954 that the following equivalent, that a set Z is approachable if and only if, and particularly this is important, every half space containing Z is approachable. Okay, and what does this kind of boil down to? It's sort of the proof of Blackwell boils down to the kind of the following picture, that we imagine we've got our average reward vector here, okay, and we've got our convex set Z, and what we can do is we can project that reward vector onto the set Z and then look at the half plane that's kind of constructed when we do that projection here. Okay, so we've got this half space. And what Blackwell says is if the expected decision that we make lies within this half, the half containing Z, if we can do that for every single adversarial choice, so let's say we're given the adversary's choice, so if we can make a decision D that lies inside that set, then in fact we can approach that set regardless of what the sequence of adversary decisions are. Okay, so we project the average reward set onto Z, take the half plane, and if we can guarantee that the reward over the next step on average is going to belong to that half plane, half space, then we can achieve approachability. Okay, all right, so that's kind of classical result. And it's also constructive results. So Blackwell actually gives a kind of proper algorithm which you could use as well. Okay. What Blackwell then shows 2 years later is you can use this for online learning. And here's the kind of setting that Michel mentioned earlier when he was talking about bandit problems and regret. Okay. So here we have the following sort of slightly shifting gears to a slightly specific problem where we can apply Blackwell approachability. We imagine that over time, we can make a sequence of decisions. We can decide to go here, or here, or here, okay? And when we make that decision, we get a reward. So at time 1, we'll get a reward, which is going to be given sort of by the height of this sort of gray line over here, okay? And what we want to do is, ultimately what we want to do is to maximize the sum of our rewards through our decisions that we make, okay? So here we're letting RT of I be the reward at time t if we make decision I, okay? And here we can imagine making some probabilities over the different decisions. And so if we made those decisions with some probability, our expected reward for decision D would just be the average of the rewards from the different arms or actions that we can take, okay? All right. So imagine doing this each time. We might not know what these rewards are. We're going to assume they're bounded, but other than that, we don't really have any information about what the sequence of rewards are. Okay. Now, the aim in online learning setting is to make a sequence of decisions that are as good as the best fixed decision. Okay. So we're not looking at the best sequence of choices over all sequences, but we're looking for the best sequence of choices that we can make and compare the reward that we get from our decision algorithm compared to the best fixed choice. So we can see here on this picture that if we always chose this last choice here, the heights are significantly higher than the other ones. And so we're going to get the most reward from that decision over here, okay, from that final decision, okay? So we can judge that in terms of the regret, okay? So that's basically comparing the average reward we get from making the best fixed decision compared to the reward we get from our algorithm over time, okay? So the regret compares the best reward we can get from a fixed decision. So we choose like 1, 2, up to the kind of final decision here, P. Okay, and we compare that with the aggregate reward we got from our algorithm here, okay? And an algorithm, a sequential decision-making algorithm, where we choose these DTs at each unit of time, is said to be the Hanan consistent, or said to be a no-regret learning algorithm, if we can get the regret to go down to be little o of t. So if we divided this by t, if this goes to 0 over time, okay? In other words, what this is saying is the performance of the algorithm is as good as the best choice, okay? amongst 1, 2 up to this final choice. Okay, and the surprising thing is that without any statistical assumptions on the rewards, okay, you can get sublinear regret to hold. Okay, and it's also surprising you can still get it to hold if you only receive feedback from the reward we choose. Okay, and that's called the multi-arm bandit problem. Okay, and you can also get sublinear regret in those cases as well. Okay. So in that context, you could think of bandit problems being a special case of the online learning outcome. Okay. And what Blackwell shows in 1956 is the following. He basically phrases that problem as a kind of vector valued game within his approachability setting. And what he does is he kind of looks at the vector of regret. So what you do is you keep a vector of how is my algorithm performing compared to each arm or each choice. So how is my choice compared to the fixed choice I doing for each component here? And that gives me this vector. And we've got Hanan consistency or no regret learning if we can get that vector into the negative orthant over here. So then Blackwell approachability would say that if I can make a decision D such that I belong to this half space, so I'm going to project my regret vector onto Z, and I get a nice half space here. If I can choose a decision that always belongs to that half space, then I can get approachability to 0. I can get this regret vector to go towards this negative orthant. Okay. So that does hold, because if we look at the change in this reward vector, it's just given by the reward of each arm I, and then we can always choose the decision D that maximizes given the choice of rewards that are there. So no matter what the adversary chooses or what the other rewards are, I can actually always choose a point within this set Z. Okay. By simply taking the decision that maximizes over all the different rewards. Okay. So since this point exists, Blackwell approachability theorem holds, and we can apply Blackwell's algorithm, and we can make a sequence of choices so that we approach this set. Okay. So that gives the following result, which is sometimes called the Hanan-Gadam theorem. There exists a way of playing the different arms so that for any sequence of actions that are decided, the average performance of the algorithm goes to 0. Okay. In other words, the performance in the game or performance in this algorithm is asymptotically as good as the best fixed choice. Okay. In other words, you're sort of learning what the best action is. Okay. Right, so that's kind of a classical result in kind of online learning. It's a consequence of the Blackwell approachability theorem. Now what I'm going to show is that a certain queuing problem and queuing algorithm is the positive occurrence and the stability of that queuing system is also a consequence of Blackwell's approachability theorem. So switching gears slightly, we're now considering a slightly different setting. Oh, Ganesh asks a question. The rewards of all actions at each time step are observable. It depends on the algorithm. I was assuming they're in that setting. Yes, they are. But in Blackwell's setting, they are. But you can do it when you only observe the rewards from one arm. If under that kind of adversarial setting, the algorithm's like X3, and there you can do that. So, but yeah, I was imagining they're the setting where you have to observe the rewards of each action each time. Okay. Okay. I'll kind of treat periodically checking the chat box as well. Thanks. Okay. So max weight and also the related algorithm called BackPressure are a kind of set of policies or scheduling policies for what's called a switch queuing network. So here I've drawn a picture of a switch queuing network. Here it's a discrete time model, and I'm going to let A, J of T be the number of arrivals to Q, J, in a queue indexed by J at time T. Okay. And I can also keep track of the queue sizes at each time. So Qj of T is the number of jobs at queue number J at time T. Okay. And in this model, we have schedules. There are constraints on the sets of queues that we can serve at any moment in time. Okay. So in particular, I've represented that here in terms of a sort of graph. So I've got 4 servers here, and I've drawn lines between the servers. And what these edges mean is that if I decide to serve, say, this server to be active, then the neighboring servers can't be serving jobs at the queue. Okay. So in particular, we've got a correct schedule here for these two green servers because none of their adjacent neighbors is trying to serve at the same time. Okay. And so we can then, in more abstract terms, we can represent this in terms of a set, a subset of the sort of positive integers or the positive orthant and the integers in order to determine some set of schedules which are allowed to do at each unit of time. Okay. So this is a pretty popular model of, say, Wi-Fi networks where there can be interference, but also internet routers. And there are also various applications in operations research areas and manufacturing areas where there's sort of some sort of server flexibility. Okay, that determines the number of departures. And within this model, we've got a decision to make. We've got to decide which schedule to use at each unit of time. Okay. Now, the max weight policy is one specific algorithm for deciding at each unit of time which schedule or which set of servers I should choose to serve. Okay. In particular, it's the following. What we do is we have a weight associated with each queue. The weight is given here in max weight by the queue size. Okay. We multiply the queue size by the number of jobs which are served at that queue under the current schedule D. Okay. And we sum those up. And once we've got that, we can maximize that linear sort of combination over the sets of schedules available. Okay. And that gives us a schedule to choose at time t, and that's essentially the max weight schedule, and that determines which jobs leave this switch queuing network. Okay. So, and there's another variant called BackPressure, which uses a slightly different weighting here. The reason for the BackPressure policy is because it allows for the possibility of jobs to leave the network and then return back into the system. Whereas in the max weight policy, it is considered what's called single hop networks. That's where once we've served a job, it has to leave the network forever. Okay. We're going to focus on max weight here, but the analysis that we discussed would go through BackPressure as well. Okay. So the nice thing about max weight is it's got good stability properties. It's good at being positive recurrent. Okay. In particular, it has what's called a maximal stability region. So I'll describe what we mean by maximal stability region now. So we're going to consider, say, this example of a switch queuing network. Let's suppose there's two parallel servers. Each of the servers can serve, there's two queues, two parallel queues. And for each of those, we've got one devoted server. And I'm going to assume we've also got an additional flexible server, which can either serve the first queue or it can move over and serve the second queue. Okay. What we can do with that is we can write down in the positive, R2 in space, we can write down the sets of services that we can do. Okay, so in particular here, the schedule is trying to serve two jobs from the first queue and is trying to serve one job from the second queue. So that would be sort of two across over here and one up here. I can write, and that's the current schedule. The schedule corresponding to do nothing would be here. The schedule which would serve one queue from each, one job from each queue would be this one. And I can sort of plot all those points. Now, the maximal stability region for this specific switch queuing network, we can construct by taking the convex combination of the schedule set. And in general, the maximal stability region is this convex combination. We just sort of plot all the points in space and then fill them in by taking the kind of convex closure. Okay. Right. And that is the largest arrival rate that the set of arrival rates that this queuing network can support. So if I had an arrival rate, which was sort of here, so let's suppose the arrivals are here, then I could construct a departure rate that lies just above it. Okay. And so as long as on average that dominated, that arrival rate that departure rate dominated that arrival rate, then we could stabilize the system. Okay. So in other words, if you give me an arrival rate, there's a way I can construct a departure rate within the stability set that dominates it, and that will give me stability. The queue sizes will go down to 0 or won't grow in time. Okay. All right, so that gives the best essentially we can do in terms of stabilizing these queues. For any arrival rate within this set, I can think of an algorithm If you give me that arrival rate, I can think of an algorithm that will work for that arrival rate. Now, the striking thing about max weight is it is stable for all of the arrival rates in this convex closure in this set over here. Okay, so that's the kind of classical result of Tacitus and Farides in 1992. Okay, what it's saying is that if there is a policy that stabilizes the network, without giving you any information about the arrival rate, the max weight can go about stabilizing the network and having small queue sizes. Okay, so that way of thinking should very much fit into the kind of way we're thinking about the minimax theorem and thinking about Blackwell approachability. Okay, under the first case, we're sort of saying, well, it's stable because if you give me the arrival rate, I can construct a departure rate that then stabilizes the system. On the other hand, what max weight is doing, it's saying, it doesn't matter what the arrival rate is, I've got a way of making decisions sequentially, which will still stabilize the system. Okay. So it's very much got that kind of flavor. And in fact, if you go through the proof of stability of max weight and back pressure, you can notice there are certain points in the proof where you can opt to use the minimax theorem in order to get your kind of convergence to zero. Okay. So what we can argue in the paper or show in the paper is the following, that if we, which is more of an observation, if you look at the queue size vector under max weight, then you can think of the decisions that the max weight algorithm is making as making kind of approachable decisions, okay, and thus implementing something where we can directly apply the Blackwell approachability theorem. So here we've taken the queue size, which is just the sum of the arrivals minus the departures, okay. And we can project that onto the negative orthant again. The negative orthant here meaning all the queue sizes are essentially zero. Okay. And just like Blackwell would do, we can construct the half space that consists, as a consequence of that projection. Okay, so over here. Now, if we look at the change in this queue size vector, the average change in it, then the arrivals minus the departures, so the adversarial decisions on the arrivals and our decisions on the departures, if we plot that, you can notice it's always going to be on this half of, in this half space. And why is that? Well, because the sort of distance from here to here is given by the maximization of the queue size vector to our decision in the scheduling set, minus the queue size vector multiplied by the average arrivals you expect in the next unit of time. Okay, so we're always going to have a decision that lies inside this half space, so long as that adversarial decision lies in the interior of that stability set. Okay, so what this is saying is is that essentially the max weight policy can be seen as a sort of instance of a Blackwell approachable policy. And as a consequence of Blackwell's approachability theorem, we can just sort of directly plug and play with that result. We get that the average queue sizes over time have to go to zero. So it must be pushing the queue sizes on average down to zero. Okay. And that's interesting because it also works on the adversarial inputs as well. So typically we assume like, Bernoulli or Poisson arrivals or things like this, queuing models. But what you can have here is you can adversarial choose the average arrival rate at each unit of time. And regardless of that, max weight is going to be able to stabilize the system. So it's robust also to adversarial arrivals. Okay. So the result there, is robust over a range of arrival rates. I must say that there are other people who have made observations of that type in the literature, particularly Michael Neely has this sort of notion of universal scheduling, which could be chosen adversarially. And one viewpoint is the reason we have these kind of robust stability properties for this kind of famous queuing algorithm is because it's essentially implementing a case of Blackwell's approachability result. Okay, so that kind of, but in some sense, we kind of think of our kind of queuing algorithm like max weight or back pressure being some sort of online sequential learning algorithm, and that's the reason that we have these kind of good stability behaviors. Okay. So here we're kind of arguing just as classical results on online learning could be seen as a consequence of Blackwell approachability. We also see that classical algorithms in queuing can also be viewed as a consequence of Blackwell approachability. And so we've kind of got this kind of direct connection between the way two fields think about learning and stability. Okay, so we can develop that a little bit more. and we're going to discuss a little bit about online learning and queuing again. For max weights, what we had is that stability was achievable under unknown arrival rates, provided it didn't matter what the arrival rates were, provided they were, and they didn't need to get told to us, provided they were inside that stability set, then the max weight algorithm is going to work for us. Okay, and that is the best you can do. Okay. However, the same isn't really true for service rates. It seems for some reason in queuing problems, you don't have this same kind of nice robustness when it comes to services. Okay, so in some sense, it seems they're parameters that we need to learn about. Okay, so so now we're going to talk about and consider the impact of kind of online learning, bandits, and other problems like this in terms of the learning of service rates. Okay. Okay, so we can go back to that picture of kind of regret that we had before, and Michel also mentioned about in his talk as well. Okay, so again, we got to make decisions about which arms or actions to choose at each unit of time. At each time we make a decision, and then we receive all the rewards we would have got at that time, or we receive just the reward of the action that we tried. Okay. And we do those sequence of decisions over time. We had this notion of regret. Okay, so how could we kind of look at that theory in terms of regret, in terms of queuing system? Okay, so one way to do this is simply to kind of take this picture and kind of flip it 90 degrees and just call it queuing system. So that's what we're going to do. Okay, so here we imagine that there's a queue, and there are jobs that are arriving, and there are different ways we can decide to go about serving those jobs. We can think of those actions or decisions as being kind of the modes of service. Okay, if we chose a good mode of service, we might get a quick service for that job. If we choose a bad mode of service, it might take us longer to serve that job, and thus the queue size is going to build up over time. Okay, so the question that comes in is, how does regret impact queues over time? Okay. And this is sort of contained in a paper that I wrote in 2014, and there are sort of related kind of follow-up works from that. I don't think anybody read my original paper, so, but certainly the different people that have looked into these things more recently. Okay, so the question is, how does sort of the performance of an online learning algorithm or a supervised learning algorithm impact in terms of queue sizes if we're trying to learn over time what's the best mode of service? Okay, so here we're going to let tau of m be the time it takes to serve the tth job to arrive at a queue under service mode m. Okay, we can let t star be, let's say, the optimal service rule. Okay, and we're going to consider policies pi, which are going to decide for each job what service mode we should use. Okay, so pi at each time is going to choose one of these m's and decide, you know, should I serve it here in this way, which would be quite fast, or should I make a bad decision in this case, in which case it would be quite slow service. Okay. And again, the regret is the performance of my algorithm, the time it takes to serve all of the first t jobs to arrive under my algorithm, compared to the optimal. Okay, and there should be some brackets here, apologies. Okay. And we're going to do this in the context of a single server queue. And what the recursion that applies to a single server queue is Linley's recursion. Okay, you can look at what the workload is like in terms of the workload just before the previous arrival. And so we have that the workload at time t is the maximum between 0, the previous workload, plus the service time minus the inter-arrival time of the jobs. Okay. All right. And what you can prove, you know, which you can prove is the following lemma, that you can sort of make a direct relationship between the workload at the queue and in terms of the regret of the algorithm that's making the decisions. Okay, so if t0 is the last time that the queue was empty, then the regret at time t+1, the difference between the workload under the policy and the workload under the optimal service rule is bounded above by the difference in the regrets, the regret at time t compared to the regret of when the queue was last empty. Okay. what this implies is that if we have an algorithm for learning the service rules, which is Hanan consistent or no regret, so we've got regret going down to 0 on average. And if the optimal service rule is stable, okay, meaning that it keeps the queue sizes close to 0 on average, or the rate of processing of arrivals of departures is equal to the rate of arrivals, so this, then we have stability of the underlying queuing system. In particular, the policy is also going to be little o of t. So in other words, good learning of service parameters, if there is a good service rule that stabilizes the system, a good algorithm for learning that service parameter should also result in a good algorithm in terms of the sequential learning algorithm. Okay, so if good service exists, a good learning algorithm will also stabilize the system. Okay. And from this, you can kind of see how other results can start to fit in. So let's suppose we only got the rewards back. Let's suppose the rewards were independent identically distributed from the different service modes, and let's suppose we only got observed the reward from the arm you chose. We discussed this in the 2014 paper about kind of bandit versions of this, and there is a result in there that discusses that. But let's suppose we had this stochastic bandit problem, okay? And let's suppose the queue under the optimal service, under the service rule, is positive recurrent. In that case, the time since the queue was last empty is going to be kind of little o of 1. And in the kind of stochastic bandit problem, we know that the best algorithms are have a regret that's about logarithm of t, and as a result of Lai and Robbins in the 1980s, which shows that that's the case. Okay. Well, if we had this being little o of 1 and this being log of t, then the difference between any log of t algorithm and the optimal service rule should be about, and this is kind of hand waving, I won't deny it, log t minus log t naught. Okay, and you can see that that's going to result in an algorithm where the difference in the performances is going to go down about 1 over t. Okay, on average in expectation. Okay, and that's essentially kind of the observation of the Krismani and Rameshihara and Shakatoya paper. Okay, so you can kind of see from that kind of earlier analysis, you can kind of understand how that analysis works out, or why it should work out. Not that we've gone through all the details that they have. Okay. All right, and the same happens in the adversarial setting and other things like this that you also discuss. Okay. Here's a slightly different example that we put into the paper, just as a kind of slightly different example, which doesn't seem to exist in the literature as things stand. So here's another way we could use that kind of earlier lemma on kind of regret and workload in queues. Okay. So suppose that we have a queuing system, a single server queue, and suppose each time a customer arrives at the queue, they give us some context, a bit like we were discussing about the revenue management example earlier. Okay, so the context means that maybe they're going on a telephone center and they have to put in some details in advance, and we receive those details. Okay, and so then when the customer arrives to the head of the queue, we can decide how we're going to go about serving that customer. Okay, we could just serve them according to service rule A, or serve them according to service rule B. Okay, we could have more than 2 different ways of serving them, but for now we'll just assume there's 2 ways of serving the customers. Okay, so we don't know what's the right way to go about serving that customer. We only know the kind of information that we've had in advance about their, if it's a hospital medical history call center, it'd be maybe some details about their account and things like this. Okay, and our rule has to kind of guess what the correct response is. So we're saying the response here is either say +1 or -1. So the information we don't know, the A or B decision, we can say that's say +1 or -1. Okay. And our policy has to make a choice based on the context we're given so far. We've got to try and guess what's the correct response. Okay. If we get it correct, if we guess it's a plus and it is a plus, then we get fast service. If we guess it's a minus and it is a minus, then we get fast service. Okay. So if we correctly guess the type of customer, then we get fast service. If we incorrectly guess the type of the customer, then we get slow service. Okay. All right. And we can consider one specific way we could go about making a relationship between these contexts and these responses. Okay. One of the easiest ways to do this is to kind of take a linear combination of the context with some weights. If that linear combination is positive, then we can say +1. If that linear combination is negative, then we say -1. Okay. This is kind of a famous learning problem, kind of class two two-part classification problem. And there's a famous algorithm for going about doing that classification problem. What we think of it is that we've got this space of context in RD, and we have different sort of pluses and minuses that we put on this space. And that vector of weights that we're using in that linear combination is giving us a decision boundary between we're going to say plus or we're going to say minus on this side. Okay. And the more correctly we label the pluses and minuses, the more correct the algorithm is going to be, and better it's going to be making decisions. Okay. There's a classical algorithm, which goes back to the 1960s, called the Perceptron Algorithm, which can be used for essentially updating these weights. Okay. So, and this is how it works here. So each time we update the weights online, given the previous contexts and the responses that we've had, we give a kind of small update. This is basically a gradient descent update and can be phrased as a kind of online convex optimization problem. We can go through that theory, which we do in the paper, and we can derive what's called the perceptron mistake bound, which is a kind of classical supervised learning result, which essentially says if there is a way to separate out the pluses from the minuses, so if there is a W star which separates out the pluses and minuses, then the number of mistakes that the perceptron algorithm is going to make is finite. Okay, and so that's kind of classical machine learning type result, and there are stochastic versions of this, and we can kind of get into kind of VC dimensions and things like this for this kind of problem, okay, but we don't do that. And in the context of that contextual queuing model, we can just directly use that perceptron mistake bound and apply it to our regret bound. What it says is that if we apply the perceptron algorithm sequentially, so we get our customers, we look at their weights, we look at if we've got fast or slow service, and over time we update those weights for each customer, then the queue size of the policy under the perceptron algorithm compared to the optimal way of serving those customers is going to be within a constant factor because of that constant bound, that constant regret bound. Okay, and moreover, you can see from that analysis, once the policy has emptied itself after the last mistake has been made, then from there on out, we're going to have essentially the optimal policy. It's always going to be choosing the correct. Okay, so there we have an example of a kind of supervised learning algorithm and how the performance of that supervised learning algorithm can lead to kind of an optimal way of serving customers in that kind of contextual queuing model. Okay, so eventually we learn the correct way to label customers and thus optimal service rule. Okay, so those are kind of two examples. First one's kind of like how do we use some classical learning stuff in the context of switch queuing networks, and then we kind of see how we can begin to kind of combine online learning ideas with some sort of simple queuing models. So obviously much more complicated things can and indeed have been done by other authors. Okay. So we've seen that there's a link between the MaxWeight algorithm and adversarial learning. We still need to learn service rates in queuing systems, and it seems that kind of good performance in learning in service rates results in good performance in queue sizes. Okay. But another important question, and we're sort of starting to get more into the kind of literature review territory, is what information should we learn? What's the right thing we should be learning about queuing systems? So sometimes we don't need to learn, sometimes, or we don't need to explicitly know what the arrival rates are, sometimes we need to explicitly do parameter estimation. And how does the information in general impact performance of the queuing system? Okay. So I'll discuss information and queues. Kwang's a little bit more responsible for this part of the talk than me, but I'll do my best to kind of go through this. So there's one way of thinking about it is in terms of what information we're going to store about the system. Are we going to store essentially parameterized information about the queuing system, trying to do a good job at estimating that? Or should we actually really be trying to think about what the state of the queuing system is and then try and increase our information about that? Okay. So useful taxonomy is contained by this paper by Ben Van Rooij and co-authors Liu et al., which is a paper on reinforcement learning called Reinforcement Learning Bit by Bit. And they kind of have this taxonomy of thinking about reinforcement learning problems. In particular, they like to kind of think of information in terms of epistemic information about the state of the system and aleatoric state information. Okay, so what is epistemic state information? Well, it's really uncertainty about the model and its parameters. So we don't, there's a parameterized class of models, but we don't know which it is. Okay, and the aleatoric information is uncertainty about the state of the model itself. Okay, so even if we knew all the parameters and all the rest of it, there are other aspects of this kind of stochastic shocks that the system undergoes, which we don't know when they're going to occur. So we don't know specifically when arrivals might occur. And so that is state information which we could use to our advantage, okay? What I'm going to argue next, this is more of a high-level discussion, is that it seems to be that in queuing systems, working a bit harder to get state information, aleatoric state information, seems to have a much bigger impact on performance than epistemic state information, okay? So go through a few examples very briefly. So an example is admission control. Here's an example of a single server queue which undergoes some arrival rate lambda, and you can choose to serve the jobs at a rate sort of 1 minus p, and then you apply sort of admission control policy where some fixed proportion over time must be diverted, okay? And there are different ways we can achieve that fixed proportion as a function, say, of queue sizes or just as Poisson thinning, and we can use other pieces of state information in order to make that decision, okay? The classical result by Stidman in 1985 proves that if we only have queue size information, the optimal policy has queue sizes which grow at log 1 minus lambda as lambda goes to p, okay? So if we get all of the information together, write this down as kind of an optimization problem, come with the optimal rule, we end up with a threshold policy. And this is the way that queue sizes can grow under that threshold policy, given knowledge of the parameters of the system, okay? So that's the best you can do with kind of epistemic information only on say, arrivals and departure rates. However, if you add a little bit more information to the system, so let's say you get information about the number of arrivals that are going to happen and when they're going to occur over the next L time units. So let's suppose you can look ahead and you can look down the road and see which arrivals are occurring. If you can use that information, you can make a big improvement in terms of the queue size performance. The expected queue size can effectively be a constant rather than growing according to this log 1 minus lambda factor. And there's a strict cutoff between those. So above some parameter region, you get this constant growth, and below that parameter region, you're essentially as good as having average parameter estimates. So it's interesting there that just a little bit more state information can have quite a pronounced effect on the performance of the system. The same holds in load balancing. So Dave Marnick and Martin Zubelir, who'll talk a bit later, have an example of load balancing where this occurs as well. You have arriving jobs to a dispatcher, and you have to instantaneously, when jobs arrive, make a decision as to which server to send them to. And they look at the trade-offs between the situation where the dispatcher can store memory about the previous servers that it's observed, and the servers can send messages back to the dispatcher about their current state. And what they find is this kind of complicated, complex trade-off between having sufficient amounts of messaging and sufficient amount of memory in order to keep the delays at 0. But what's interesting is there is a strict threshold here between a regime where you don't have enough memory or you don't have enough messaging and a regime where you do. And when you do, you have 0 queue size, and when you don't, you have queue sizes that can grow, okay, or can be positive, okay. Earlier examples, you know, I like to include the example of dynamic alternative routing. So AT&T used to keep track, like to do dynamic alternative routing of their telephone traffic in the sort of 80s and 90s. And what they do there is kind of get average arrival estimates, apply them to, and service estimates, apply them to a queuing formula, and then do kind of a static optimization to determine what proportion of those telephone calls should be alternatively routed. Okay, so you basically try and estimate average arrivals, estimate departures, get call lengths, get all the information you need, get those averages and optimize for that. Okay, that turns out to work much worse than a system where you just simply use loss as an indication of when you should be thinking about doing alternative routing. So you basically just run the system as usual, and as soon as the direct route doesn't work, you do an alternative routing. And if you kind of a little bit careful about how you can do that, you can come up with a system that performs significantly better than the system working with average parameters. Okay. And the same holds for switch networks. So just that example that I mentioned earlier, you don't have to have complicated examples. That one with the flexible server, if my arrival rate is here and my departure rate is there, if I did random, so that's halfway between here and here, if the server randomly decides to be here or here, that probably have about double the queue size between the one that just jockeys whenever there's 2 jobs at one queue, okay? So something that's aware of the state of the system, got improved state awareness, is actually better than something where you know the average arrival rate, okay? So again, there's not a big kind of formal theory there, but I'd argue that the examples suggest that it's better to gain good state information and optimize subject to the current state rather than statistically estimate state parameters and then optimize for that. It doesn't mean there isn't an advantage in knowing those parameters, but it does seem that kind of getting a little bit more information about the current state of the system seems to have a bigger effect. Also, it seems from these sorts of results, there tends to be thresholds between good and bad state descriptions, and that transition seems to be quite a sharp transition. So that's something that's quite interesting from the recent literature. I've only got a few minutes, but I'll quickly discuss about kind of reinforcement learning and queuing systems to finish up. Okay. So this is kind of reinforcement learning in one slide. So reinforcement learning is kind of an area of machine learning. The idea is you have some agent or some algorithm that's got to make decisions. It's going to make actions, they call them actions, okay? And then you've got some environment. It's usually, for modern machine learning, unless it tends to be a simulation environment, but it doesn't have to be. And from that system, the agent is then given back observations and rewards of the state of that system, okay? If the state evolution is a Markov chain in terms of the previous state and action, and if the same holds rewards, then if we know the reward distribution and probability distribution for state evolution, then it's called a Markov decision process. And the objective of maximizing the sum of rewards over time can be written quite neatly in terms of this Bellman equation here. So here, the optimal reward series we can get over time satisfies this fixed point equation here, okay? And that assumes we know all the things that are going on inside this expectation by knowing these distributions. However, if these aren't known to us, then they need to be estimated somehow, okay? And this is when the model isn't known, this is what called reinforcement learning. So instead of getting this fixed point equation, we have to try and approximate it. So here we can use a stochastic approximation procedure called Q-learning in order to estimate what the actual value of that is and make decisions, okay? And often, because the sets of states and actions can be quite large, people often apply some sort of function approximation to these estimators. So we take some function, we might say we assume that the Q function here, this function is linear, for example, and then you can also apply these sort of same fixed point equations there. Okay. One thing to say about it is, so sort of reinforcement learning feels like a separate area. Actually, you know, from the very beginning, a lot of the early work on reinforcement learning has already, you know, been applied in queuing systems. So, you know, one of the classical results is this kind of TD Gammon algorithm of Trejaro, you know, which really kind of is essentially what, you know, DeepMind and companies like this do day in, day out. You know, it really started with this paper in 1992. And not long after that, you see people applying like neural networks and things like this to different application areas in reinforcement learning. So as early as 1996, you see things like people optimizing queues in a network of elevators in order to kind of optimize the service of customers. Okay. Also, kind of the first textbook on kind of using neural networks for reinforcement learning, which I've got a copy here, is Bert-Sekus and Sicklitz's 1996 book. You see other applications, for example, Bert-Sekus looking at in terms of dynamic channel allocation, job shop scheduling problems, and also the first application of the cross-entropy method in terms of policy search reinforcement learning gave an inventory control example as its main example. So this is kind of an early proto kind of policy gradient algorithm. Okay. However, as much as there is that kind of early literature there where queuing has been applied in reinforcement learning, there's still a lot of theoretical challenges in making essentially the theory of reinforcement learning work for queuing theory. I think of kind of like reinforcement learning, thinking of games like kind of Snakes and Ladders or something like this, or you know, large finite state spaces perhaps, but not thinking about the kind of specific issues that can occur in queuing systems in terms of the theoretical results. So issues that can occur, and I'll say that even this early paper of Kreitis and Bartow really does a great job of articulating the kind of challenges that occur in queuing systems. And we, you know, we're kind of now, there are people looking at these again. Issues of having an unbounded state space, because queues can usually go off to infinity. Potentially unbounded costs, because we care about queue length and delay. So if the queue size is bounded, then the costs are going to be undelayed. Making reinforcement learning algorithms and reward optimizations work with stability guarantees, okay? And even when we do have stability guarantees, it could be in a heavy traffic scenario. In this case, the time for the system to refresh itself can be very large. Something which kind of bounds on performance of reinforcement learning algorithms don't cope well with. We can have non-stationarity over time. Queuing systems, particularly in communications, are often working in a decentralized environment, very large distributed systems. Because a lot of algorithms in reinforcement learning currently train via simulation, there is also this big question of when you move something from simulation to reality, is it going to work as well as you thought it would? Not unsurmountable, but continuous time modeling. Queuing systems are often modeled in continuous time, and usually if they're in the real world, they exist in continuous time. And then also finally, as we discussed in the last part, we don't always have complete state information, or the state information that we need is an important consideration. And so we might not be able to model the underlying process of the Markov process. And like I say, we organized this workshop in the summer. You can check out, there's a web link to that in our paper, and also you can sort of grab it on reinforcement learning and networks and queues, and just quickly review some of the papers that turned up there. So we're quite pleased with the kind of showing we got, and please do check out the papers that appeared. We've had a couple of recent papers that are essentially by Devarat Shah and Mandiano and Jiaomin Ji, particularly looking at issues around infinite state space and stability guarantees. So can we get a reinforcement learning theory to work in an infinite state space setting, provided we can get some sort of Lyapunov guarantee? We have an excellent paper by Kuhn, Wyman, and Lee, which look into decentralized coordination. They're sort of saying, like, if we do local decision rules, they're saying that actually if we do local reinforcement learning, it can be within a constant factor of the global optimum. So I think that's a fantastic result. Dai and Glusman have done a lot of very interesting work, really trying to deal with this kind of infinite large cycle times, large costs, and how can we get, say, policy gradient algorithms to work in that setting, and improvements of those so that they might work much better for queuing problems. Slightly differently, a fantastic paper, Dika, Josh, and Squante look at how we can use queuing formulas to improve gradient descent algorithms and optimization algorithms for queuing systems. I haven't seen much more in that area since. I really think there's a lot of potential there. In terms of bandits, also, and some data center work, Shay Mena and some of his co-authors here, particularly Mohan, is looking at sort of bandits and how you can use that kind of theory to work with queuing systems. And also, there are cases where we have queuing systems where we know closed form solutions, such as inventory control. And there's a recent paper at Argual where they look at how the regret perturbation analysis can follow through there. Okay, final thing, I'll maybe stop after this, but the problems that are there don't stop you implementing reinforcement learning algorithms. So here's some work that I'm also affiliated with the Alan Turing Institute, and here's some work that we did over the course of the year. So we eventually implemented some sort of deep reinforcement learning agents, and I'll show you a quick video here. This is us applying a kind of neural network reinforcement learning agent to a sequence of junctions. So sort of coded all this up, just got our favorite deep reinforcement learning algorithms, policy gradient algorithms, and different deep Q learning algorithms. And we can see that we can actually come up with an algorithm that seems to be making the right decisions over time, and we can train it, and within 15, 20 minutes, we can get something that's a quite well-performing reinforcement learning algorithm for a sequence of junctions in a road traffic network. So this is a commercial simulator called Visim. We were fortunate enough to talk to the Transport Research Laboratory in the UK and get access to simulators of the Mover system, which is the system for traffic junction control used across the UK. And we can see that within we can basically train, if we look at the load here and the queue length, our deep reinforcement learning algorithm is significantly better than the kind of commercial system that's used in the UK currently. And there are some companies that we've chatted with, Vivacity Labs in the UK, which look at implementing these types of systems. And Alvaro, the student on the project, has interned with them and done some work with them. So it doesn't mean that you can't apply things, if you see what I mean. So I think that's very much what learning and queuing theory and data-driven queuing theory should be doing, is that we've got these fantastic models that work in a reasonably kind of closed form environment, but like in a road traffic junction, there are aspects of the model that we can't account for well. We're not very good at writing down a closed form queuing model for the slowing down and the speeding up of vehicles. And so those should be features of our model that we're trying to learn. And then on top of that, we should be trying to then put on our queuing theory models, which we know are going to stabilize the system, are going to give us good performance. So kind of where I see the kind of where learning theory can and sort of data-driven applications would be very important for queuing systems. And like I say, there's a load of applications that are here and simulators that one can use. And yeah, I think I'll stop there because I'm going to run over otherwise. But yeah, that's kind of overview of the things that we've discussed so far. So I just want to say a big thank you to everybody for listening, and you can grab a copy of the paper that discusses all of these topics on the archive as well. So thank you.
Thank you so much, Neil. That was brilliant, and really aligned a lot of the classical results with these modern techniques that are coming up more and more. And just at the end there, to get your perspective on where we're at is also really helpful. So I think we can take some questions in these last few minutes before we close the session. So if you'd like to put up your hand, we can give you audio or pop something in the chat. So please go ahead if you're waiting. I guess in the third part of your third theme about the role of Michelle, hang on. Do you want to jump in, Michelle?
Yeah, if you want to ask a question first, please go ahead.
Okay, sorry, it just popped up. I'll ask a quick one, which was in the role of information. In your paper, you kind of talk about the availability of the predictive information like future arrivals that can help improve performance. So it's kind of general question, but what's your intuition about other types of look-ahead information that could be available and might be helpful in terms of performance improvements?
Well, anything to do with future arrivals and states is always going to help you a lot. The question is sort of when to use it and what's the right kind of rules. Unfortunately, I think the kind of state of affairs is kind of fairly particular anecdotal examples, but it seems to be, let's say you had a learning algorithm that you were implementing. I probably work quite hard to get as much information as possible about, say, how much of the future arrivals of those jobs, as much as you can, essentially within a given, say, resource or performance guarantee in order to get the, get the performance up. So I think that seems to be the right way to go about things. Say, rather than, and the contrast I'm trying to sort of make there, well, maybe Kwang's trying to make it more than me because there's a little bit more. It'd be nice if he was here and I could get him on the call. But rather than kind of getting quite a sophisticated algorithm that's, say, trying to estimate average arrivals, if you just got a little bit more information about future arrivals, that might work way better, if you see what I mean. So statistics about current information, things that can impact you quite close in time, seem to make a bigger difference than the average that's over a long period of time. I think that's a general rule, and I think that's particularly important in, say, our reinforcement learning work there with the traffic systems. One of the reasons that Mover doesn't work so well is because it uses loop detectors, and so it's basically trying to get an idea of is there a car or not. It's getting this kind of bit stream. Whereas if you're starting to kind of like maybe use like a camera to detect there's 3 bikes here in a bus and one of them's accelerating, then you can do way more with that and have I don't think that works better because we're particularly good at coding up neural networks or things like this. It works better because there's better state information and then you're just trying to apply out the box things to leverage that essentially. Yeah.
Excellent. No, thank you. I'll throw over to Michelle, please.
Well, in the first place, thanks very much for this wonderful lecture. Second place, I had a question about the max weight part of your talk.
Yeah, sure.
So can you say a little bit about what aspects of max weight actually make it work, or phrase differently? So what will be the class of policies for which the same type of results carries over?
I mean, yeah, okay, so we thought a little bit about that. It's not clear in general of which application areas in general are going to work with that. Blackwell's original results very much kind of based around a kind of quadratic Lyapunov function type of approach, which is also what MaxWeight is based around. That said, the reason both work under these kind of adversarial and more robust, I think, is because they both share this kind of approachability property. if you look at online learning algorithms, they have the same Blackwell condition, and they have versions of it using potential functions. If you look at that same analysis and apply it to max weight, you arrive at these kind of F max weight. We apply a function to the Q size and then use that. So the online learning algorithm equivalent would be this potential function approach, and the potential function approach for that is this kind of F max weight policies as well. So you can kind of see that actually those two things match up as well, if you see what I mean. So definitely there are extensions that get made in the learning literature correspond to extensions that we know about in the max weight examples as well.
Okay. Well, thank you very much.
Yeah, cheers. Oh, I enjoyed your talk as well, Michelle.
Excellent. So we should wrap up the session just for time. So Neil, thank you so much for your tutorial and all your contributions. And so I'd like to thank all three speakers for the first session of the workshop. It's been a brilliant start. And so as I close the session, I'd like to remind you that in 3 hours, session 2 will begin wherever you are. And this is our keynote session where